Hi everyone, we're going to have a look at sample H now. So for sample H, when we try the unsaturation test, we find that the orange colour remains. And this means that we don't have any carbon-carbon multiple bonds in our molecule. So we don't have a double or a triple bond, so we're not looking at an alkene or an alkyne functional group. When we do the oxidation test, using the orange potassium dichromate, the solution turns green. So this reaction means that oxidation has occurred, and we will either have an alcohol, so a primary or secondary alcohol functional group in our molecule, or a carbonyl group, particularly an aldehyde, rather than a ketone, because ketones don't always, in this case, don't undergo oxidation. And then if we do the carboxylic acid test using sodium carbonate, we don't have any bubbles, so we don't have any carboxylic acid groups. Next, we look at the IR, remembering that from about 1500 downwards is what we call the fingerprint region, and isn't that interesting. So we're going to be looking from 1500 upwards. And we don't see anything in about 1500 to 2500 range. Then we hit our carbon-hydrogen rotation vibration range. So this would be carbon-hydrogen vibrations. Moving on from the carbon-hydrogen bonding, we move upfield where we see this very significant, easily identifiable signal. And it is very broad. It is for our alcohols, the OH vibrations, typically between about 3000 to 3500. So this tells us, in the first instance, that we might have a primary or secondary alcohol. So let's keep that in our head while we move on to the next slide. The next thing I look at is the mass spectrum, particularly so I can pick out the mass of my molecular ion, which should help me identify the molecular formula I'm dealing with. As we know, we always go to the end of the spectrum, so the highest up we can get where there's a signal, because this is our molecular ion peak and will tell us the mass of the molecular ion, which is 60. Now, we do have another peak that's very close to it, sitting at about 59. However, this is probably not due to any halogens because the ratio isn't quite right, and the difference in mass is not quite right either. Using what we have found out so far, and you might at this stage want to check your carbon NMR spectrum as well to tell you how many carbons there actually are in your molecule. For a molecular mass of about 60, this gives us 3 carbons, 8 hydrogens, and 1 oxygen. Again, here we don't have a 1-to-1 or 3-to-1 molecular ion peak ratio, so we probably don't have chlorine or bromine in our molecule. To double check that we really do have 3 carbons, we have a look at the carbon NMR, so 1, 2, 3. And at this stage, you can think about the placement of the signals on the spectrum, so whether they're downfield or upfield. Given we have quite a simple molecule, the carbon NMR probably isn't going to give you much help. But if we are thinking about this signal out here, which stands out at about 65, this is typically a carbon that is bonded to an oxygen, either an alcohol, ether, or ester. So this just reinforces the idea that we have an alcohol functional group in our molecule. Now, the proton NMR, which is where things get exciting. So we know we have an alcohol. We don't know where it sits. We know we have a carbon chain that is 3 carbons long. So let's draw in what we know so far. We have a carbon chain that's 3 carbons long. I always start at this end of the spectrum, upfield, because the easiest peak to identify is this peak here that's a triplet with 3 hydrogens making up that signal. And almost always this is a dead giveaway for a CH3 group that is next to a CH2 group, because we have the triplet from the 2 neighbouring protons, and it's always downfield, unless of course it's next to a carbon that has, say, more electronegative element attached. So this is probably a CH3 group, and it's one of the easiest things to start drawing your molecule off with. And it's next to a CH2 group, most probably, given the signal. So we've almost assigned two of our signals already. This CH2 group here is next to an unknown number of protons on this carbon and 3 on this side. So it's probably going to be some kind of multiplet. So we would expect it to be this signal here. This signal here has 1, 2, 3, 4, 5, 6. As a splitting pattern, it's a sextet, which means that the central protons probably need to be next to 5 other protons in order to get this sextet splitting pattern, which means that our alcohol is on one of our terminal carbons. If we keep moving down our NMR spectrum, we come to this triplet signal here, which integrates for 2 protons, which is probably this set of protons here, because it's next to this set of protons, so 2 protons would split this signal into a triplet. And then finally, where do we see our OH proton? That's usually downfield shifted due to being next to an electronegative element. And it's usually a broad signal because this hydrogen here pops on and off in the deuterated solvent, which means that the signal ends up being quite broad. So this signal here corresponds to our alcohol OH. So if we were to assign which signals are which, we'll call this 1. So this will be 1. We'll call this environment 2. And another way to rationalize this environment is that these 2 protons are on a carbon that's attached to an electronegative element, so they will be de-shielded and shifted downfield. Then this proton environment here would correspond to this signal, and this proton environment here would correspond to this signal. And the last thing we need to do is give this molecule a name. It's really important to specify where the alcohol is when we name our compounds. So here we have 3 carbons, so we're dealing with some kind of propane, propanol. And the alcohol is at the 1 position. 1, 2, 3. Where the alcohol is attached takes highest priority. So this is how you might go about assigning one propan 1-ol. What would it look like if we had our alcohol in the middle of our molecule? How might our NMR spectrum change? And you can think about this when you're assigning spectra, and it's always good to double check your molecule and make sure it makes sense. And think about if the molecule had a functional group moved, how would the NMR spectrum change? Just so you can check that you've got the right structure. So if we look at propan 2-ol and think about how our structure might change, well, we would still see this OH signal, but then we would only have 1 hydrogen here. We would have a line of symmetry, and then we have a CH3 group here and a CH3 group here. They're both next to 1 hydrogen. So we would expect them, and then they're both next to a carbon that has an electronegative element attached. So we'd expect to see them shifted a little bit above 1, possibly. And they would be a doublet, and they would be the same. So it would integrate for 6 protons. And then this hydrogen here, being next to 6 protons, would be a septet, sitting somewhere down between 3 and 4. So that's how the NMR spectrum would change if we had propan 2-ol instead of propan 1-ol. I hope you found that explanation helpful, and I hope you're finding generally these series of explanations helpful as well.